Okay, let's see. Oh, are we recording? Yeah, we're recording. Okay, good deal. So here's where we were last time, and we were talking about various applications of. We're talking about various applications of integrals, and so we were talking about this formula right here. This is our general formula for finding the center of mass, sometimes called the centroid, anyway, of a region. And let's see. Oh, and I forgot to do the door thing. Sorry. Okay. So, remember, the point of interest about this expression is in how you compute it, right? That expression, you can compute basically one coordinate at a time. Just because of the nature of the expression, we're multiplying by scalars, we're adding, we're dividing by a scalar. All of that's done one coordinate at a time. Okay, so let's apply this to an example. And there's a couple of computational little points of interest in this example. We've got a domain given that's the upper half disk. So this region right here. And given radius, given density, I'm keeping the density as 1 just to make the integral work out more conveniently. Based on these assumptions, let's compute the location of the center of mass. And as we saw up here, we're going to compute one coordinate at a time. Now, do be aware, I'm sure y'all are already hep to this point, but here I called the coordinates x1 through xn. Here I'm calling the coordinates x and y. Doesn't matter. Right? The point is one coordinate at a time, and when you're calling your coordinates x and y, this is what it looks like to do the first coordinate, and then likewise, this is what it looks like to do the second coordinate. So this is really just a matter of kind of plugging into that existing formula. The question that we now face is how do we compute these two things? And you can see, of course, what I'm going to do right here in the notes already. By the way, notice that as we wrote down this first integral here, it did not announce itself as, by the way, you can compute that with a symmetry argument, right? So this is something you have to notice, right? So just make sure that you're always on the lookout for this. Proficiency with symmetry arguments doesn't do you any good if you don't ever notice that you can do the symmetry arguments, right? So you have to always head on a swivel, always looking for symmetry in your domains, right? So when you see a domain like this, very quickly you should be thinking, oh my God, look at that. It's symmetric over the y-axis. Isn't that nice? I wonder if maybe I might get lucky and maybe the integrand might be odd as well and I can actually use one of these symmetry arguments. Totally awesome. And in the first case here, this integral right here, it does. Now, nice exercise to supply those details. Make sure that you can do that. Again, don't forget, you can't just say equals 0 by symmetry. Be nice if you could. By the way, just for humor value, I'll point out that when I was in college, there was more than one situation that happened to me where I was taking a test and I had, 15 seconds left, and I had an integral I was looking at, and I didn't have time to think it through, and okay, equals 0 by symmetry, and then walk away and fingers crossed and hope for the best, and I scored more than once. Right? So that was cool. I was happy about that. But let's take a quick moment. Did I deserve those points? Nah, I was guessing. That was a wild guess. Right? So I think it's reasonable, as an instructor, to if I'm going to give points, I need to establish that you actually know what you wrote, and so you do have to supply those details. And again, I've documented 5 specific points that we look for with symmetry arguments. So do make sure to supply those. Okay. All right. So the second integral. Now, no such luck here. You might call this a landmine question because the domain is symmetric, right? And you're going to be very tempted to look at this integrand and think, oh, that looks like an odd power, right? And get excited about that as well and try to make a symmetry argument here. And of course, that's crash and burn. It's not odd over the only symmetry of the domain that we can even entertain, right? So we got nothing there. There is no symmetry argument to be made in this case. Again, easy way to refute any possible temptations you might have to make a symmetry argument. Remember, symmetry arguments are based on cancellations, right? And you can't have a cancellation if your integrand is never negative, right? And you look at this domain, our integrand's never negative. Certainly not half the time negative. So out of the question, couldn't possibly be a symmetry argument. Okay, so how are we going to compute this integral? Well, here's a couple of choices. You can do your differentials in either order, and plug and chug, off you go. Which one of these is a better integral to compute? And this is just, again, computational sort of strategery. Arguably, this is a discussion appropriate for section 5.2, 3? I can't remember, one or the other of those when we're talking about double integrals. And which one of these is easier? I like to make the following observation, and I think this is a good thing to be on the lookout for. And it's hard to see this before you write down your two options, right? But sometimes, especially when you're dealing with square roots, which we are here, notice your very first antidifferentiation is going to make the antiderivative constant times y squared, which when you plug in the square root, will make the square root disappear, and it's all polynomials all the way down after that. Right? So this second integral, I think, is really nice. This is a much more desirable integral to compute than the one above it. The one above it, it's fine. You can totally do it, but you will end up with having to do a little substitution, and there's little details to be checked when you do a substitution, and it's just slightly, harder. It's not that bad, but all else being equal, it's kind of nice to keep your eyes open and always pick the easy option instead of the hard option. Does that make sense to everybody? All right. Okay, so moment of inertia. This is a physics idea, and this is not a physics course, right? So I'm going to try to focus as much as possible on what I consider to be the math-relevant ideas here. And real quick, just so we know what we're talking about, the idea is that we have some sort of an axis, and then we have something that's rotating around that axis, and you can talk about the velocity as it rotates, and you can talk about the angular speed. In other words, not distance per unit time, but angle per unit time as it rotates. And you can talk about how much kinetic energy it has as it's rotating around. It's going to have some velocity, and mass that has velocity has kinetic energy. And so how would we compute that kinetic energy? And, 1/2 mv squared, yeah, sure. Unless your region is large. And the issue that this brings up is that as this thing, I imagine that I've got some big thing tied to a string, and I'm rotating it around like this, right? So as you do that, this piece of mass right there is going a lot slower than this piece of mass, right? Oh, those look kind of the same, don't they? Let me, how about, oh gosh, what's not going to, I think these are all going to look kind of the same. They're all going to turn into mud. Okay, here we go. So the one that I have here on the inside is in a given single rotation. It only moves a short distance, whereas this other one, in that same amount of time, it moves a much greater distance. So this particle of mass on the outside is literally moving faster. Even if these two little chunks of mass have exactly the same mass, this one's got a lot more kinetic energy, right? So we can't just write down 1/2 mv squared. That doesn't account for the fact that v varies importantly, significantly over our large solid. So the big point that I want to make here, and by the way, please consider thinking through the algebra that I'm going to kind of gloss over here. It's physics, right? So, whatever. But here's the big idea. Kinetic energy is an accumulating quantity. It's another example of an accumulating quantity, and we haven't used it as an example previously of a accumulating quantity. We've computed stuff like mass and population and work and et cetera. But kinetic energy, we just haven't done that yet. So this, what I have circled here, is the, I think, reasonable observation that the kinetic energy of the whole lump is the sum of the kinetic energies of the little pieces that you would chop it up into. And that's purely a physics appeal. This is just another kind of quantity where the whole is the sum of the parts. On which then you can argue that kinetic energy is 1/2 mv squared because on each little piece is small, which means all the mass of that little small piece is pretty much at the same location, not exactly, but pretty close. And so you can refer to all of its mass as just dm, and you can refer to its velocity as just, whatever the velocity is at that point. Okay, and then, yada, 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 details. So, look through that if you're curious. You don't have to. It's not deep water. It's just some details based on above. Here's the punchline. The punchline is that the formula for kinetic energy is this, but which is much more conveniently written like this. And let's take a quick moment to recognize how nice it is to write the formula for kinetic energy like this. It looks a lot like 1/2 mv squared. It really does, right? The difference being that this thing that's playing the role of V isn't V. It's not distance per unit time, it's angle per unit time, and so I'm going to call that kind of an angular analog of speed. It's angle instead of distance, but still, in some sense, change of location per unit time. Just, angle instead of distance. So let's kind of put it all together then. We have here an angular formula for kinetic energy that is highly analogous to the linear formula for kinetic energy in terms of its structure. This is the angular analog of V, speed. Doesn't it kind of stand to reason then that whatever this thing is here, that's right there in the formula where mass would have been for the linear formula, wouldn't it be reasonable to call that the angular analog of mass? I think that's a really natural and nice way to think about this. So that thing, the thing that's I in that position, and notice that's just a placeholder for this expression right here, that is an object very naturally of interest when you're talking about rotating things and kinetic energy, and you want to use a very natural looking formula like this. This thing plays the role of mass, kind of, but pretty naturally. So this formula, integral of r squared dm, is an important object of interest, and the common word for this is moment of inertia. Is that cool? Okay. All right, so it got a little physicsy there for a second, but as far as we're concerned in this class, what you need to know is that right there, that there's this thing called moment of inertia. It's important in kinetic energy arguments, and it's an integral over whatever your domain is, whatever your solid, wherever your mass is. It's an integral of r squared dm. So make sure to memorize that formula, integral r squared dm. Okay. Now, there is a subtlety here that we do need to discuss, and that is that this r, you'll notice in my picture here, that r is the distance to whatever the axis of rotation is. So very importantly, this is not necessarily the cylindrical coordinate r. There's only so many letters in the alphabet. Some of them get used more than once for different things, right? So I'm sorry to say R is used a lot in a lot of different ways. So you got to constant head on a swivel on that as well. Just be on the lookout. So in this case, this R is referring to whatever is the distance from x comma y comma z, whatever your point is, to the axis that the rotation is going to be around. So it's different for different situations. If you're rotating around the z-axis, then distance from wherever you might be to that z-axis is the usual good old cylindrical coordinate r. And cool in that case, right. But if you're rotating instead around some other line, so there's a line it's not the z-axis, it's not even parallel to the z-axis, it's not even an axis, right? There's just some line. It happens to be parallel to the x-axis, right? But some line there, right, like that. We would need to have a formula. We would need to figure out how to compute distance from arbitrary x comma y comma z to that line, that perpendicular distance. And in this case, it works out not so bad because this happens to be parallel to the x-axis. That makes the calculation work out very nicely. In this case, that's the formula, not that. Right? Everybody on board? A couple other examples. Sometimes it might happen to be that the mass in question is entirely confined in, let's say, the xy plane. Nice when that happens. Right? And maybe you're rotating around the y-axis. Now, this is still kind of a three-dimensional problem because that rotation is still in 3 dimensions. I mean, you're rotating around the y-axis. Right? It's not around the origin. It's not through the y-axis. Right? So, again, you still have to think it through. Now, because your points that you're looking at are entirely in the xy plane, you can draw that same picture. It's still distance, but in this case, it's just very convenient to write down that distance is literally just the absolute value of x. So the geometry is different in every example, right? And I urge you, please don't try to memorize a single formula that will always be the right answer. I guess technically it's possible, but it's very inefficient at best. Please also don't try to memorize a finite list of cases because there's too many. It doesn't make any sense. That also is very inefficient and also very unreliable. It's a question of time. You're going to forget at least some of those formulas. Give it time, right? So in the long run, I think the best strategy is just to remember that you need to interpret R as the distance from XYZ to whatever your axis is, and then look at the geometry of that situation and write down the distance on the basis of that geometry, treating every example as its own special case that has to be considered. Okay. Alrighty. Okay, so a quick example here. We are going to look at let's see here, this domain on which I have mass distributed like so, as indicated by this formula, delta. So notice that's a weird formula. The density is higher and then lower and then higher again, right? This is weird distribution of mass in this region. And we want to find the moment of inertia. So standard first thing to write down, integral r squared dm. It's always integral r squared dm. The integral is appropriate to whatever the domain is. Double integral in this case, triple integral that we wrote down previously for, assuming we were talking about a solid region. But whatever is appropriate to the domain, it's always integral r squared dm. Okay. So with that noted, let's see here. we can talk about dm. Mass is density times area, and good news, the density was given. So that I can just plug right in. Right, dA, of course, can be dx dy or dy dx. Suit yourself. Then I've got to figure out what this r is. And again, this is an always kind of situation. You've always got to look at the picture and think about, okay, well, yeah, but what's my r? What does r need to be to make sense in this particular application? Well, it says right here we're going around the x-axis. There's the x-axis. Whatever little piece of mass I have that I want to think about, how it rotates around that axis, that given axis. What's the distance from that little piece of mass to our axis of rotation? Well, that distance in this case is just y, and it's tempting to say absolute value of y, and that would also be correct, but then you notice that y is always positive on this domain, and so we could just say y for free. Is that cool? Is everybody with me? Okay. So r is y. And then it's all over but the plug and chug. At this point, here's our double integral. Oh, you do have to slice up the bounds. So this gives you these bounds, start doing the integrals. And you're going to notice that there's a couple integrals that pop up here that are a little bit tricky. You got to make sure you remember how to do those integrals. This is the kind of stuff that I think is perfectly reasonable, fair game expectation. In this class, that you should make sure to be able to do this kind of integral. So it's a nice little exercise. Make sure you can do that. All right? Everybody happy? Okay. That does it for Chapter 5. So we are going to move on. Now, I guess I'll recognize it real quick. Oh, let's see. Did I pop that up? Oh, I didn't pop that up yet. I'm going to recognize. Why don't I just do this? Where's my... okay, there we go. I'm going to recognize that, we do have an exam on Friday. Right, I'm sure y'all remember. It's on the class schedule and all, right? We've been, noting it here and there in the last several class meetings. And this, what we're talking about today is not fair game for that exam. Right? So in that sense, you don't have to worry about it. But more to the point, you don't have to worry about what we're doing today in the extremely short term of, next couple of days. Right? So that said, the end of the semester is actually also approaching pretty quickly. Right? If you look at the calendar, it's not that far away. And this is definitely going to be fair game on exam 3. And on the final exam, and these are important ideas, and so anyway, this is stuff that does matter. Just feel free to take a little flexibility on focusing on this stuff. If you want to wait till after the exam to focus on this Chapter 6 stuff, sure, but it's definitely something you want to give a little attention to. Okay, so we're going to address here now a kind of a sophisticated question, and that is, how do we deal with weird context domains? Right. So let's discuss what we've previously considered. Long ago in Calc 1 classes, y'all talked about integrals on the real number line. So you have an interval. Right? An interval is a one-dimensional domain, and it was confined to a one-dimensional world, namely the x-axis. Then we talked about double integrals. Okay, now all of a sudden we have two-dimensional domains. Very conveniently, these two-dimensional domains were confined to the two-dimensional xy plane. Likewise, triple integrals, three-dimensional solids, but in a three-dimensional world. They've always been what I'm going to loosely call dimensionally appropriate, right? Dimensionally convenient. Well, not everything is, right? So, for example, let's think about a curve. Well, let's do it like this, a curve in the plane. So here's an example of a curve and it is in the two-dimensional xy plane. And can I do an integral on that domain? And if so, what on earth does that mean? Right? And how in the world am I going to compute that? Let's just remind ourselves why we did integrals in the first place. What was the purpose of an integral? Right? Why do we bother with integrals? And again, forget about area under a curve. That's a special case of marginal interest. Right? The reason we do integrals is because we're interested in accumulating quantities. We're interested in computing stuff that, when you chop it up into little pieces, the whole is the sum of the parts. Can there exist circumstances where we're interested in how the whole might be the sum of the parts when it's distributed over a curve in the plane? Well, yeah, of course. Yeah, sure, why not? Right? I could have, for example, we in single variable calculus classes, you talk about the mass of a rod, right? You have a one-dimensional mass, right? And it's along the x-axis, and how do you compute that total mass? Okay, yeah, fine. Well, what if you have a bent rod? You might still want to compute the mass of that also, right? So we find ourselves in this circumstance where we might want to do accumulations, whole of the sum of the parts arguments, chop it up, add it up, arguments, on a curve in the plane, or possibly a curve in 3 dimensions, which of course would be a very similar looking picture, just with a third axis there, right? Or eventually, I might even want to know what happens if I have a surface in space, a 2-dimensional surface. And we're gonna deal with that part later. But right now, let's focus on curves. Here's the big idea. The whole will continue to be the sum of the parts. We're going to add up a bunch of little pieces as we slice more and more finely to make round-off errors go away. And on each little piece, right, so we're adding up over the entire thing. On each little piece, if I ask, okay, yeah, but how much, whatever this quantity is, be it mass or population of ants crawling around on this thing, or work that it takes to blah, 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 whatever it might happen to be, how am I going to understand on each little piece? And what we're going to prepare for, and what is typically what we're interested in for integrals, is where we can talk about stuff per unit size times size. And again, copycatting from every other integral we've previously written down. Your integrand is always quantity per unit size. Your differential is always representing size. Right? This applies to single variable integrals, double integrals, triple integrals. The nature of what we mean by size, appropriate to the context, of course, but always stuff per unit size times size. So in particular then, the differential here is length, and that means that our integrand, whatever that thing is stuff per unit length. Is that all right? All right, so wouldn't it be nice if we can compute these things? How in the world are we going to compute these things? And we'll get to that momentarily. I just want to point out that this is an idea that applies in a lot of different, there's a lot of different applications of this, and we're going to be doing a lot of stuff with this construction, and since that's the case, it is nice to have a shorthand and a lingo to represent it. So here's the shorthand, and here's the lingo. This is called a scalar line integral, and we use this notation. I think this notation's very natural. We use a differential to represent the fact that this notion of size we're writing down here are always little pieces of length. We've used S to represent length before, so ds is a natural notation. Our integrand, okay, yeah, whatever, you just kind of put that there. And then we use a single integral symbol to represent that we're adding up in a limit. Again, very standard shorthand that we've seen in other contexts. So very believable notation. Oh, also notice that the domain, whatever your domain is, subscript. right? So that is an indication of over what region, in this case a curve in the plane, over what region are we adding up stuff. Okay, is everybody happy with this notation? Okay, let's talk about the terminology. Integral, sure, of course, obviously. Why do we call this a line integral? I think it's a little dated, a little unfortunate at this point, right? The intention was that a curve is there is a different use of the word line that refers to anything you can draw with a pen, right? So, line drawing, for example, doesn't necessarily mean straight line. So it's a little bit confusing. In particular, this does not have to be a straight line. This is just a reference to the fact that the domain's a curve. Would it be a little preferable if this were universally understood as a curve integral? Yeah, probably. Some people do call these path integrals. But that's a little bit more narrow. Line integral, I think, is the more common term. Okay. Now, why scalar? This I'm not going to be able to give you a particularly persuasive answer to just yet, but it turns out that there's going to be another kind of line integral that we're going to talk about actually very soon, possibly today. That's optimistic. Probably Monday. But there is another kind of integral, another kind of line integral, and it is importantly different from what we're looking at here. It's a more sophisticated object. Scalar in this case is a reference to the seemingly obvious fact that our differential is a scalar and that our integrand is a scalar. The next kind of integral the next kind of line integral we're going to write down is going to be not that, and details will come later. Okay, so I like that our book uses the clarified term scalar line integral. Okay, so how do you compute these things? We're going to rip off an old idea from change of variables. Change of variables is a strategy where we say if you have a domain that you don't like, by the way, let's take a moment to recognize, I don't like this domain. I don't know how to compute on this domain. This is not an interval on the x-axis. I can't just kind of do Calc 1 on this domain. Calc 1 doesn't recognize any notion of non-straight interval. It just doesn't, right? So Calc 1 doesn't help us with this. It's also, even though it's in 2 dimensions, it's not a double interval because there's no area in this picture. So we do not have tools for how to compute this. And again, I'm going to say that we, don't like that domain. So what do we do when we don't like a domain? What did change of variables do? Change of variables says that view it as being an image, presumably an image of something that you like better. And by the way, it sure would be nice if I could, view this as an integral on literally an interval on the, let's say, the t-axis, something like that. Wouldn't that be awesome? Because we're experts in how to do these kinds of integrals. If you have an integral on an interval on the t-axis, yeah, Calc 1, we're loaded with tools. So we're just going to try to figure out how to find a way to view our curve as being an image of an interval. And good news, we already know how to do that. That's called a parameterization. Lucky break. Actually, let me say it differently. Not so much a lucky break, but we did all that stuff with parameterizations largely so that we would be able to have the tool that we needed at this moment here. So, by the way, all that stuff that we did with parameterizations way back at near the start of the course, this would be a really good time to review all that stuff. Make sure that you polish up, I guess would be the right word. Polish up all of those skills. Make sure that you're good to go on how to parameterize things and what is a parameterization and stuff like that. Okay. And when you've done that, then you can indeed pull back through the parameterization all we have to do in order to do the pullback, aside from plugging in, right? Obvious substitution of this variable for, certain formula for certain variables. That's just plugging and chugging. We just need to figure out how to make sense of the stretching factor. In other words, I need to know if I'm looking at a little piece there of size dt, I need to be able to talk about a little piece here of size ds, and I need a relationship between ds and dt. And this is actually a pretty easy argument in this case. ds is already known to be a factor times dt, because ds is a distance, dt is a time, and distance equals speed times time. And speed, of course, is the magnitude of the velocity factor. So, again, lucky break. We already have the stretching factor formula that we need. Is that going down okay? Is everybody happy with that? All right. Sweet. Well, we just keep getting lucky. So our scalar line integral, our brand new tool for how to compute dimensionally weird integrals, it pretty well addressed by just saying ds is magnitude of x prime times dt. Don't forget to plug in, right? I mean, whatever your parameterization is, that tells you how to plug in. Well, you know what? I'm going to do it like this. I keep missing. Okay. That tells you how to plug in for your x, y, and z in your original integral. And then, don't forget to compute the stretching factor, magnitude of the velocity, and off you go. It's single variable plug and chug at that point. Totally doable. All right, now before I show you an example, I do want to address a concern. There is a worrisome arbitrariness to what I did here. So we started with a curve, and I said, okay, let's parameterize it. And a reasonable complaint, when I say, parameterize it, a reasonable complaint would be, which parameterization? There's lots of parameterizations. There's endless, countless parameterizations of this one single curve. Which parameterization should I use? It looks like the value that I'm going to get, it clearly involves the parameterization. Maybe different parameterizations would give me different answers. That's a serious, legitimate worry, right? And so I just need to address that point, and it has a very happy answer, and that is that it doesn't matter. You're always going to get the same answer no matter which parameterization that you use. The above expression is independent of the parameterization. So go crazy. Do whatever you like. Whatever's most convenient, typically, nice choice. It does not matter. Okay. All right, so let's do one. Here's a scenario that we already kind of entertained. We're thinking about an irregular, not a metal rod on the x-axis, but a bent metal wire. It's kind of like a rod, but maybe a little thinner, right? Bent around in some way. And I want to compute for example, I want to compute the mass of this thing. We'll just start with the mass. And I have some specifics of how the wire is curved. It's curved according to this parameterization. That tells me exactly how the wire is curved. And by the way, here's how mass is distributed on that wire. It depends on the location per that formula. So in some places it's more mass per unit length. In some places it's less mass per unit length. Does everybody see the scenario we're trying to address? All right. Well, just in preparation for what we know we're going to need, we know we're going to need the stretching factor. We know the stretching factor is the magnitude of the velocity. So we can just say I'm going to use this parameterization that I was given, so why not? And take the derivative, take the magnitude. That's plug and chug. You just got to do it, right? And your stretching factor is going to be that. So I do that initially just because I know it's going to come up. I know I'm going to need it, and so why not go ahead and get that part out of the way. Okay. All right, and then how do we finish up the details? Well, mass is an accumulating quantity. This wire, bent around however it may be, the whole is the sum of the parts. That's how mass works. Mass is mass per unit length times length on each individual piece. ds, don't forget, ds is stretching factor times dt. Don't forget also, we've already computed that stretching factor. We did that up here in anticipation of needing it. Everybody with me so far? Everybody's happy? All right, so there's one remaining detail, and that is what in the world do I do with the x and the y here? The x and the y are kind of sitting there. How do I deal with that? Easy thing to lose track of, easy thing to forget. But the parameterization being basically the change of variables function that we're using here, the parameterization is literally telling us x and y. It is literally giving us position in the xy plane as a function of time as we trace out how this wire is sitting in the plane. So we have, given the parameterization, we have explicit formulas for x and y. So given that, x is t and y is t squared. Quite fit there, does it? Okay, there we go. Everybody on board with that? Okay, and last thing, what are the bounds for the integral? Well, we need to integrate over the whole thing. The whole thing is traced out by these values of t, and so our range of values of t, 0 to 1, again, just kind of given in this case. Everybody on board? Single variable calculus ensues. Now that is an annoying integral, and but y'all know how to do integrals. Okay. All right, now back up real quick. Notice the question actually asks us for several things. It asks us for the mass and the center of mass and the moment of inertia around a certain axis. So, oh my gosh, we've got to do a whole bunch of separate calculations here, and each one of these, of course, will be a different calculation, but each one of these will use a lot of the same stuff. Each one of these calculations is an accumulating quantity that's done over a domain. That's the same domain. That's parameterized by the same parameterization over the same values of t. Mass distributed by the same density formula. The parameterization having the same velocity and therefore the same speed. A lot of these calculations is exactly the same stuff. Just a little bit different, right? But a lot of sort of duplication. So for example, here's the calculation for moment of inertia, integral r squared dm. Again, it's always integral r squared dm. You just got to interpret what kind of integral it is appropriate to the dimension of the domain. And, well, mass is still density times size. The density is still x plus y. Size is still speed times dt. Speed is still that. It's all kind of the same range of values of t. A lot of it's just rip off of the same exact stuff. Oh, and then by the way, we've got the same formula for x, and we've got the same formula for y, which we have to use a second time because, an extra factor of y shows up because we're doing, in fact, a different integral here. So, yeah, so the resulting integral does end up looking different, right? This is definitely a different integral from that, but the analysis of how you break it all down, there's a tremendous amount of overlap there. So that's kind of convenient. Everybody good? All right, here's another example. This is manufactured, but not entirely nonsense. So I've got a plot of land, the boundary of which is the unit circle, and on this unit circle, I have a fence, and the fence is sitting right on top of the unit circle, like so. Okay, you want to put a fence around your property? Sure. You want to let the dog off the leash? That's cool, whatever. Okay, now what's weird is the height of the fence is not constant. Here, the height depends on the location. Now, why would you do such a thing? Well, okay, manufactured example, right? A little bit unnatural, but again, not the craziest thing in the world. You might want more shade in part of your yard, right, where you like to sit. You might want less shade in a different part of your yard, maybe where your vegetable garden is. Right? So, not the craziest thing in the world at all. So anyway, that being the case, we've got this plot with a boundary line and a fence on top of the boundary, and we want to compute the total area of the fence. How are we going to go about computing that area of the fence? Alrighty, so I start with, as usual, accumulating quantity. Area is an accumulating quantity. The whole is the sum of the parts. The total area of the fence is the sum of the areas of the pickets, you might call them. These little strips of fence. I'm just going to call them pickets. Cool. Little differential pickets. Each one of those little differential pickets, it's pretty easy to write down the formula for that area. The area is going to be, the height times the length of the base, which is, of course, ds. And so, again, I think no surprise, particularly that dA is h times ds. Again, right there in the picture. Is everybody on board so far? Okay. All right, so off we go now. We have a scalar line integral to compute, and the way we compute scalar line integrals is step one, we parameterize. Right? We're basically going to do something kind of like a change of variables. It's not technically a change of variables the way we set things up. The dimension has to be preserved if we're going to use the term change of variables, but it is morally equivalent to a change of variables, and so we have to view this as an image, so we have to parameterize it. And our domain being the unit circle, how do we parameterize that unit circle? Well, pretty standard choice. Pretty easy to compute the derivative. Pretty straightforward to compute the speed, namely the magnitude of that velocity being the derivative. Yeah? Everybody with me? That's the stuff that we're going to need along the way. So now we kind of just start plugging in the ds, speed times dt. Conveniently, again, we've already computed that speed is 1. And so our ds simplifies just like that. Right? We are given explicitly in the statement of the question, we're given that height as a function of position is that. And again, the sneaky, elusive, easy to forget last little plug-in aspect of things here is what is x? We've got this x sitting right there. What's the deal with x? Well, again, it comes out of the parameterization, and it says so right there. X is cosine t. Remember, when you're pulling back through a parameterization, through a change of variables function, whatever, when you're doing a pullback, that function that through which you are pulling back tells you how to plug in for your coordinates x and y, or x, y, and z, or what have you. So x is cosine t. And lo and behold, we end up with an easy single variable integral here, totally doable. Y'all can plug and chug that through, and that'll be your answer. And this makes for a great stopping point. So we'll draw the line right there. See y'all on a Friday. Good luck studying for the exam. Yeah, see you then. Okay, have a good one.